안녕하십니까. 저는 이상훈 교수님 연구실에서 석박통합 과정으로 재학 중인 박재우 학생입니다. 발표 시작하도록 하겠습니다. I am pleased to begin my presentation on design of core interface to enhance induced electric field gradient for magnetic nerve stimulation. In this talk, I will cover the background of the research, the key objective and method for designing the core interface, and the result and implication of this study. Neurostimulation is a cutting-edge medical technique that modulates the nervous system. It's a powerful tool for managing chronic pain, restoring neurological function, and treating various nervous system disorders. This technology can be categorized based on the target area of the nervous system. First, peripheral nerve stimulation. This target peripheral nerve located outside the brain and spinal cord. It's commonly used to treat localized chronic pain or to enhance motor function. Next is spinal cord stimulation. This focuses on the spinal cord. It helps manage widespread chronic pain, especially in the back or limbs. Lastly, deep brain stimulation. This method targets the specific region within the brain. It is widely recognized for its success in treating neurological conditions. Neurostimulation technology primarily uses electrical stimulation to modulate nervous system activity. This involves delivering controlled electrical signal to nerves, which depolarize the nerve membrane and generate action potentials. However, it does have limitations. Electrical currents can lack precision, leading to off-target effects. Another issue is implementation. Prolonged electrical stimulation can cause tissue irritation and immune response. To address these issues, magnetic stimulation has been proposed as an alternative to electrical stimulation. Magnetic stimulation uses rapidly changing magnetic field to induce electrical currents in the target tissue without direct contact. This method is non-invasive and can be more focused, reducing the risk of target stimulation and tissue damage. While it offers several advantages, magnetic stimulation has its challenges. Limited penetration depths making it less effective for deep tissues. Spatial resolution can still be a concern, especially in complex neural areas. Power limitation may require high energy to stimulate larger or deeper areas. Coil heating, which can cause discomfort or safety concern during prolonged use. Size and portability of the coils making the system bulky and less convenient. So our research goal is to develop a neural interface that can address these limitations. As the first step, we designed the coil interface targeting the peripheral nerves. As shown in figure, the proposed coil interface is different from conventional coils. Unlike traditional systems, our design can be implanted directly on the nerve surface. This allows us to achieve higher resolution and smaller size, and this could serve as a crucial breakthrough for the development of more efficient magnetic stimulation interface in the future. Our research is organized into 4 key stages to develop the core interface. The first stage involves defining the geometric parameter necessary for the core interface design. As shown in the figure, we select the parameters such as the angle, pi, theta, and the distance between the coils. In the second stage, we conducted a theoretical analysis of the membrane voltage, which is critical parameter for nerve stimulation. The membrane voltage in peripheral nerves under magnetic stimulation can be derived using the following equation. The key parameter here is the gradient of the induced electric field, which plays a crucial role in effective nerve stimulation. The third stage involved fabricating the coil determined from simulation. We utilize both 3D printing and hand winding techniques to create the core interface. Finally, in the fourth stage, we validated the electrical characteristic of the core interface and confirmed its ability to stimulate the nerve. The induced electric field gradient and magnetic field were calculated using commensurate FEM frequency analysis. The coils were placed on cylindrical nerve model with a distance of 50 micrometer between the coils and the nerves, as shown in the figure. We simulated various coil shapes and found that the diamond-shaped coil was the most effective design. To further investigate the influence of coil placement, we calculate the induced electric field gradient when overlapping the diamond structure. The placement was divided into 12 steps, each with a 0.25 mm difference. The direction of the current is represented by the black arrows. The result indicated the most effective placement occurred in phase P1, and we conclude that the optimal coil spacing is 25 micrometer. The following figure shows the location of the induced nerve stimulation, which is centered between the coils. The next simulation was performed to reduce the coil's resistance and size by trimming unnecessary sections. The figure shows an example of this process. We calculate the induced electric field gradient for the coils that were cut both horizontally and vertically. Following this, we adjust the overall ratio to finalize the optimal size. The results are as follows. The design that shows the highest electric field gradient is depicted in the figure. On the x-axis, we have the current intensity, and on the y-axis, we can see the size ratio in the heat map. The ratio of 0.5 and 0.75 yield the highest electric field gradients. If the size of the coil is too large or too small, the external components of the coil counteract the current, reducing the effectiveness of stimulation. The coils were fabricated as follows. We made the coil-shaped model using a 3D printer and wound the coil by hand using a copper wire of 50 micrometer in diameter. The size was determined to be 0.75 size factor level because 0.5 size is too small to make precisely using a hand. The fabricated coil is shown in the following picture. Wires were wound around each mold by 50 turns, considering the direction of the current. Finally, we tested to see if it can cause stimulation by applying it to the sciatic nerve of the SD rat. The rat was anesthetized by isoflurane, and the target area was incised to place the coil. We tried to simulate the main sciatic nerve and measure muscle signal from TA and GC. Similar parameters are shown in the figure below. The parameters for electrical and magnetic stimulation were selected separately. The results of magnetic stimulation were shown in the video. Muscle signals were observed in TA and GC. In the case of magnetic stimulation, a stimulus artifact was observed in all cases, as shown in the blue circle. The core interface was small enough to be placed in the sciatic nerve, and the same maximum muscle signal saturation could be observed when compared to the electrical stimulation. In the conclusion, we conclude that the norm of the magnetic field does not necessarily follow the same trend as the induced electric field gradient, and closer spacing between coils in the four-leaf coil arrangement is shown to be favorable for field focusing. And the main geometric elements for coil design were identified as line segment aligned with the nerve axis. And by optimizing the coil design, we successfully stimulate the sciatic nerve in the rat by creating a coil interface with a size of 6.2 mm by 2.2 mm. This research provides a guideline for coil interface design in peripheral nerve stimulation and demonstrates a novel approach to enhancing induced electric field gradient. Thank you for watching my presentation.